Okay, good afternoon everyone. Welcome to your second session of the day here at Probabilistic AI. My name is Andrew Johnson and I'll be giving your section today on Bayesian workflow. I'm a postdoctoral researcher at Aalto University with Aki Vetteri, whose name some of you might recognize from a lot of Bayesian work. And I'm also a developer for Stan, the probabilistic programming language I'll be talking about today. So you might find that I'm a bit biased towards Stan, but I'll do what I can. So just to briefly summarize what we're going to be touching on today. So before we can really get into the nuts and bolts of what a Bayesian workflow is and how we apply a Bayesian workflow, we kind of need to lay this foundation first of what is Bayesian inference, what does it mean to think like a Bayesian, and also some of the technical details of how these Bayesian models are estimated, because they play a really key role in these workflows that we follow. After we've covered that foundation, we'll start to talk about the concepts behind what a Bayesian workflow is, why we think they're great and you should follow them, and also give you a bit of a practical introduction to how we might apply a Bayesian workflow to an actual real-world analysis. To follow along in this latest session with the step-by-step workflow, we do have a Colab notebook available in the online ProbAI repository for today. You'll find it under my name in the day one sessions, and so we'll be able to work through that together later this afternoon. All right, so why Bayesian inference? Why is it important to take a Bayesian approach to some problems? Well, really the idea of Bayesian inference aligns quite well with how we naturally and normally think about the world. You know, you don't normally come to a situation with absolutely no preconceived assumptions, ideals, or knowledge. You come in with years of experience, you have societal expectations and assumptions that you've built up. And based on these assumptions and what you then observe in front of you, you combine both of those and you update your internal model about the world. So when it comes to a Bayesian model, that's pretty much exactly what we do. We want to account for the fact that we do have this external knowledge, prior assumptions, prior information, and we want to combine that with what we observe in front of us. And it's not just some black box that we see. It doesn't exist in a vacuum. There is all of this other information. And additionally, it's a very powerful tool to be able to quantify and reason about uncertainty in our models and our analyses. Because just because we've observed something in one sample, it doesn't mean that it's true for the entire population, doesn't mean that it's true for all samples. And it's really powerful to be able to say, well, I have this level of certainty or uncertainty in my inference. And it's really important to be able to account for that and reason about it when you're making conclusions or basing future decisions off these models. Now, when it comes to Bayesian inference, over the next few days, you're going to be getting a lot of statistical and mathematical background. You'll probably end up seeing Bayes' theorem in your sleep by Friday. So hopefully to have something that sticks with you a little bit differently, I'm going to try to motivate this from a bit more of an applied perspective, and considering the ideas of personality and psychology, because my background is psychology. So as a bit of a practical example of what it means to think like a Bayesian, some of you might have seen this video by Grant Sanderson or 3 Blue 1 Brown, which uses this example of predicting whether someone is a farmer or a librarian. So for example, let's say you've met a person, we'll call them Avery, and you're asked to guess whether Avery is a farmer or a librarian. Completely false dichotomy, but there is no other choice. They are the one or the other. And you're asked to say, which one are they and how confident are you? So at this stage, we come to these data, these observations, and we have none. We don't know anything about Avery, anything at all. And we also don't have any prior information or any prior assumptions about what it means to be a farmer or what it would mean for Avery to be a farmer. So when it comes to making our prediction or applying this model, we then say, well, Avery's equally likely to be both, and we don't really have any confidence in which one that they are. So if we were to try to depict this idea of uncertainty graphically, it might look something like this. So we can see along our x-axis, we've got the probability that Avery is a farmer. For 0, they're definitely a librarian. 1, they're definitely a farmer. And then on the y-axis, we have our level of confidence in each of these predictions. You might recognize that I've very sneakily stuck in this idea of a posterior. This is our posterior distribution of the probability of Avery being a farmer. And really that's all a lot of this is. It's about identifying, it's this combination of prior assumption and observations to get a joint considered inference. All right, so right now we have no observations and we have no assumptions. But what happened if we learned a little bit more about Avery? What if we had Avery complete a careers questionnaire and we questioned some of their friends? We find out that they do prefer a more structured and organized life, and they do prefer things to be quiet. Now, at this stage, we still don't have any assumptions, we still don't have any prior information, but now we have more observed data to sort of inform what our prediction should be. So naturally, we're going to predict that Avery is more likely to be a librarian. It sounds like it suits them a bit better. How confident should we be in this prediction? Would anyone like to hazard a guess? 50%, 80%? What do we think? All right, well, I'll just show you. So while we might now believe that the probability that Avery is a farmer is small because it doesn't fit their personality, we might still be wrong. So we don't want to encode a lot of certainty in this idea. So we have our graphical depiction here, where now we're applying more weight to the lower probability of being a farmer. We have more confidence here. Just to say, I have truncated these plots, so they might look nonsensical, but it's really just to graphically show you. All right, so that's what happens about our beliefs when we have more observations. But what happens, on the other hand, if we have more prior information, more assumptions? So what if we had some idea about the probability of just anybody being a farmer? How would that affect our predictions? So at this stage, what if we knew some international occupation statistics? What if we knew what it was like for anybody to be a farmer? So we can see that there are dramatically more farmers worldwide than there are librarians. And really what that says is that regardless of your personal interests, you are more likely to be a farmer than you are a librarian. So once we take into account this new prior information that we have, we might then update our prediction, our model, to then say, well, based on this, Avery is more likely to be a farmer. But then this introduces another question. These are worldwide international statistics. How much certainty do we want these international statistics to introduce into our predictions? How much influence do we want these priors to have? So if we consider just the global probability of being a farmer, we might then say, well, Avery is more likely to be a farmer. But because we don't know where Avery lives, we don't really know how appropriate those global statistics are. Just because a country with a high rural area might have more farmers than librarians, that doesn't mean that someone living in the center of Helsinki or London is more likely to be a farmer. So we want this prior information to inform our conclusions, but we don't want it to have a lot of influence. We don't want it to have a lot of informativeness. So that's a very quick example of the idea of different levels of informativeness in your prior information. Not everything has to be equally influential. But on the other hand, what if we wanted something that was more influential? What if we had more accurate data? So let's update our observed data model so that now we collect more information about Avery, we collect more information about their personal habits, and we find that Avery really likes libraries. They really like to read books. That's how they like to spend their time. So now we have very strong observed data. We have a very strong observed likelihood of Avery being a librarian. So because our observed likelihood is now quite strong, and we weren't giving a lot of weight or influence to our prior information, well, that observed data is then going to have more influence than our weak priors. We're now going to conclude that Avery is more likely to be a librarian. And because we have a lot more confidence in these observations, we're going to give more weight, we're going to give more certainty to those conclusions and those predictions. We're going to have a lot more confidence that Avery is likely to be a librarian than they are a farmer. But then on the other hand, what if we had very strong prior information, very strong prior assumptions? How would that change our conclusions? So I said we can't use our global statistics because we don't know where Avery lives. So what if we were both, Avery and ourselves, were both living in, let's say, Denmark, in Australia? It is a real place. That's where my dad grew up, about 5 hours south of Perth. It doesn't seem real, and it's still confusing for me to be here, but yes. So Denmark is a small country town in rural Australia, population less than 10,000, and their primary industry is agriculture, so dairy and grain farming, as well as a fantastic wine region. Take that, France. They only have one library, and they already have 2 full-time librarians that have both been there for more than a decade and are really very unlikely to leave. So we now have some very, very strong prior information that, well, regardless of Avery's personality, regardless of what Avery wants to do, if he wants to be a librarian, if they want to be a librarian, it's very hard for that to happen in Denmark. So there's this extra societal, cultural information that we have that says, regardless of these observed data, it's very unlikely that Avery is going to be a librarian. And now, because we have such strong prior information, to be able to override these conclusions and say, well, Avery is more likely to be a librarian, we would then need even stronger observed data. It might be that we find out that one librarian is going to retire soon. We find that Avery is actively plotting to get one of them fired. Country Australia is quite rough. So really the key things to take away here is that when we're taking a Bayesian approach to Bayesian inference, we are considering both what we've observed, but also all the prior knowledge about a situation that we have, about our expert knowledge, and even just about the model itself that's being analysed. Your prior information, it doesn't have to be, cultural norms, it doesn't have to be population statistics. They can be statistical assumptions that you use to identify a model. And the other key thing to emphasize here is this idea of strength of influence and certainty in these. So if one of them is weak, if your prior is weak, then your observation is going to have more influence, and vice versa. So it's very important to consider the 2 of these when you're combining them and building a Bayesian model. All right, so this is the formula that you're either very used to or you will be getting very used to this week. So when we look at this idea of Bayesian inference, so really what we're estimating is this quantity here. So this is our posterior distribution. So the probability here, theta, our parameter, so that's the probability of Avery being a librarian. And what's the probability of that given our observed data? And we estimate that using our prior knowledge. So these are our cultural norms, population statistics, expert knowledge. And we also consider our likelihood, our observed data. So it's the combination of these 2 that give us our final conclusion. But just because we know what we want to estimate, it's unfortunately not very easy to directly estimate this. So because we want to make inferences using this posterior distribution, we want to reason about the probability of Avery being a farmer. Unfortunately, with a lot of our models, it's not available in this closed form, easy to specify distribution. Some of you might be familiar with the concept of things like conjugate models or conjugacy, where a combination of a prior and a likelihood does give you a nice analytical distribution. However, as you get to more complex models, that really isn't the case. So when this happens, we go towards a more numerical approximation, and this is a Markov chain Monte Carlo. I won't talk about this too much because you do have a whole session on it later this week with Charles Margosian, also a Stan developer, just going to say that. So MCMC is a really powerful tool for computing these expectations or these functions over our posterior, and they've really revolutionized a lot of Bayesian inference. I'm a native speaker. So, when it comes to Markov chain Monte Carlo, the key component here is the Markov chain. So this is a sequential set of samples. So you start with a proposal, and then based on that proposed sample, you take another sample, and another, and another. Different sampling schemes will have different methods for making these proposals. We call them a Markov transition. If you want to know more about them, that's the term to look up, a Markov transition. And given enough time, these sequential sample transitions will eventually quantify our target distribution. So when we say that we want to take a Markov chain Monte Carlo estimate or something, that's where we're applying our target function to this sequential set of samples and taking the expectation across them. Pardon me. So to put it in more concrete terms, so given our target distribution, given our posterior that we would like to estimate, what we do is estimate our Markov chain. So we take n sequential samples. We start with our proposal. We get another one and another one. After we've taken our n samples, we apply our function of interest to this Markov chain, and we take the expectation across it. And it has been shown that as this Markov chain, as the number of transitions in this chain tends to infinity, our expectation converges to the true expectation, what that true value would be if you had exactly the posterior distribution, not just an approximation of it. To show that in a different concrete way, let's say, for example, you had a simple bivariate normal here as x and y shown as a contour plot. Now, while you can see the distribution here, in reality, you don't have the distribution there. You don't know what it looks like. You don't know where it is to sample it. It's just an empty parameter space that you're trying to sample. So what we do with Markov chain Monte Carlo is, well, we start our sample at some point, and then we start our transitions. So we can see that as the chain starts, we take a few samples, and then eventually our chain starts to find our probability mass, our target distribution. So we can see on the right here, we have our estimate of the level of bias in our estimate. So here we have the true, our unknown true estimate, and up here we have our Monte Carlo estimate. So we can see that at the very start of the chain, we have quite a bit of bias. There's quite a difference between the true and estimated value of our function. And you can see that's because, well, a lot of these samples aren't even from our distribution of interest. Now, once our Markov chain has found our probability mass, after a few more iterations, it starts to explore it. And we can see our bias in our estimates start to decrease towards 0 as we're starting to more accurately quantify this probability mass. And then as the Markov chain continues, it explores it even more thoroughly. And eventually, asymptotically, it converges to the true estimate. So there's two concepts that I want to emphasize here. There's two key sources of bias. So first and largest is at the start of this process of finding the probability mass. It looks quite simple here in this small two-dimensional space, but as you get more and more parameters, as the dimensionality of your parameter space increases, your probability mass can be geometrically atrocious and very, very hard for a sampler to find. And the second source of bias is the thoroughness within which the sampler has explored this parameter space. So if you only run your sampler for a few iterations, even after it has found your target distribution, you still have non-trivial bias there because there are still aspects, still tails of the distribution you might not have explored. So when we move on to our actual practical workflow stage, these are two things that we will be sort of coming back to on how we diagnose these and how we handle these. All right, before I move on to the next step, did we have any questions around Bayesian inference and this computational aspect of Bayesian inference so far? So the question was, can we evaluate a function on the posterior? Because we don't have it, we can't evaluate a function on the posterior, but we're evaluating a function on samples of the posterior. So it's still the same function, just being applied to each of our samples. Mm-hmm. So this is our bias. So the f and the e of f here is just any arbitrary function. This might be a mean, it might be a variance. And we have our true value of our expectation here, and we have our estimate of that function here. So we see that as our Markov chain fully explores, as our Markov chain better sort of captures our distribution, then our estimate is much more accurate.
Using this MCMC sampling, can we only estimate the mean of the posterior, or can we also approximate the variance of the posterior? Because the posterior would have a non-parametric.
Yes, so it's any function over the distribution. So this can be a quantile of the distribution, it can be the mean, it can be the variance. It's just you have a function that you're applying to the samples from the distribution. You're not just estimating the mean. You'll see a bit more when we get to the applied examples of the different things that we're computing. Okay. All right, so to connect to this idea of sampling and so using an MCMC sampler. So right now we have a fairly trivial, easy case. A bivariate normal, 2 dimensions, very easy to explore. But as with a lot of real-world analyses, you are working with much more complicated models. You might have many, many, many more parameters, or you might have very complex models that you can't work with in as easy way as a simple distribution like this. So in order to allow MCMC sampling to be a bit more efficient with these either higher dimensional or very complex geometrically posteriors, extensions to MCMC sampling were developed. Oh, pardon me. So the main one that I'm going to touch on quickly is Hamiltonian Monte Carlo. So this is an extension that's often sort of described as a scalable approach to Markov chain inference. So as your dimensionality of your parameter space increases, the probability mass of your distribution is then getting pulled between all these different dimensions, and it's quite hard for a sampler to both effectively find the probability mass in such a high-dimensional, sparse parameter space, but it also becomes quite difficult for the sampler to effectively explore a very geometrically tricky probability mass. It's hard for it to sort of jump between all these different dimensions. So the extension that was proposed with Hamiltonian Monte Carlo uses the gradient of our target probability density function. So rather than something like Metropolis Hastings or Gibbs, which works with conditional values, we're instead working with our probability density function and our gradients of that, and using that to inform our sampler where the regions of high probability mass are. Now, while this was quite effective in a lot of cases, it does require the specification of these tuning parameters to help sort of different stages of the sampler guide how much it moves and how quickly. And a lot of the time, these tuning parameters, they're quite unique to the posterior at hand. It's not a very sort of generalized, flexible approach. So while it's quite powerful, it's not something that you can just quickly pick up and apply to your problem and just be confident that it's going to work quickly. To help expand this, there was a self-tuning version of HMC proposed called the no U-turn sampler. And this so-called nut sampler, it uses our warm-up, our adaptation phase, to help tune our Hamiltonian Monte Carlo parameters so that we get the benefits of this guided, informed exploration without having to know in advance what our tuning parameters are, without having to personally customize them iteratively to our own distribution. And it's this algorithm that is being used in STAN, which is what we'll be using later in the next section. So to give you a very quick crash course in STAN, so STAN is a probabilistic programming language, which you can use to sort of express and estimate these models. It has a lot of different algorithms. So the ones we'll be using today is NUTS, so the self-adapting Monte Carlo. But you can also use it for gradient-based optimization, approximate inference using both ADVI and Pathfinder, which is a new algorithm that was proposed a couple of years ago, and also approximate sampling using Laplace approximation. Pardon me. Now, some quick prefaces before we expose you to the STAN language. It can be a little bit different to a lot of the probabilistic programming languages that you might be familiar with so far. And really one of the key things that a lot of newcomers can struggle with is that STAN is a strongly statically typed language. So every variable, it has to have a type, and we can't change that type, and we can't change that type once we've declared it. And when it comes to STAN, you don't always have to sort of express your model using a lot of these loops or map functions. A lot of our functions are natively, we call them vectorized. And this allows you to be, pardon me. So this allows us to take advantage of both a lot of the hardware mechanics of estimating multiple values together, but also it allows you to reuse a lot of expensive computation. So for example, when we come to some of our multivariate likelihoods, you don't want to have to invert a covariance matrix for every single observation. You just want to do it once and then use it for your entire array of observations. So when you are first exposed to sort of seeing a STAN model, it can look quite different to what you're normally used to. And the other really key difference that can be quite strange is that STAN is a compiled instead of an interpreted language. So if you work with something like Pyro or JAGs and bugs, you just specify the model, and then you give the model to Pyro, JAGs, bugs, and it runs and it just interprets the commands. STAN, on the other hand, has to translate your model to C++, and that C++ is compiled to machine code. This has benefits and drawbacks. So on one hand, there is a large benefit to this idea of reducing overhead. Only the code we need for our model is included and is executed. So there's a lot less extra setup or unnecessary preparation. And also modern compilers are extremely good at optimizing code for both your specific machine and also for even just inefficient programming. They will actively reorder and combine terms to make things as fast as possible without affecting your inference. However, it does come with some fairly large drawbacks. So having to recompile a model when you change it, it does take time and it does use up, it can use up quite a bit of RAM. So for people that like to very quickly iterate through different models, it can be quite difficult to work with. Additionally, of course, it means you need a working C++ toolchain. And if anyone's had to compile C++ on Windows, you know that's a horrendous time and a lot of tech support for Windows and STAN. And all of this means that it can reduce accessibility for new users. Regardless of that, I still love it. So. All right. So before I duck onto the Bayesian workflow side of things, do we have any questions about Hamiltonian Monte Carlo and STAN?
2 slides ago, you mentioned that
Oh, sorry. It's not combined, it's an alternative choice. You can either do sampling or you can do gradient optimization, gradient-based optimization, sorry. So you're not optimizing within your sampling.
Related to that specific part, I would imagine that optimization falls under the creation of inference. We have it as a separate bullet point.
Yes, they are slightly different algorithms. So while optimization is you're minimizing a loss function, with variational inference, you're trying to have an approximate distribution that can represent your posterior. Oftentimes it's a multivariate normal, but it's not always the same idea of minimizing a loss function. You're trying to have a good approximation, but it might not be minimizing a loss function specifically. Kind of. So in the Slack channel for the day, I'll also pop up some extra resources on the different algorithms that are used. Hopefully that'll answer your question. All right, so now that we've covered a lot of this foundation around what it is to think like a Bayesian and what it is to estimate a Bayesian model, how do we actually take that information and turn it into a model? How do we take what we know and what we observe and build a model? And then also, once we build it, how can we be confident that what we've done has been maybe not the right choices, but at least good enough, robust, defensible choices? And this is where the idea of a Bayesian workflow comes in. So as hopefully you already know, or you might come to appreciate this week, Bayesian inference is incredibly powerful. You can do quite a lot that you can't do outside of a Bayesian framework, but it comes with a lot of inherent complexity. So you have multiple options for the prior that you choose, the likelihood you choose for your outcomes, and you even have multiple ways to specify the same prior and likelihood. And different specifications can lead to very different sampling performance. And that's something that we'll actually explicitly touch on later in the session. So because there is a lot of this complexity, and you might find that you've made the wrong decision at some point, or you might find that the result just isn't what you expect, and then you start making decisions. You start, well, I'll change this prior, I might try a different family. And you just sort of build up this series of really just ad hoc decisions of how you ended up with your final model. And that can lead to a lot of questions around, replicability, trustworthiness. How do we know that the steps that you made to end up with this model were, robust and defensible? And it wasn't just you adjusting your model to find something that aligns with what you expect, what we call researcher degrees of freedom. So for a process like this, we need something systematic. So we need something that is evidence-based, built on steps that you follow. But it also needs to be flexible, because Bayesian modeling, it is complex. You have a lot of different decisions you make, and we can't prescribe a system that everyone follows the exact same way. So when we talk about Bayesian modeling, so really there are three key stages, or at least three that I'm going to touch on. So you have this first stage of you're building your model. You then are making inferences on the model that you've estimated and the quantities that the model has estimated. And from there, you can be checking on the quality of your model. If you find that the quality isn't acceptable or satisfactory, you might be improving your model or even just throwing it out completely. Now, each of these stages covers quite a few different sort of steps and problems that you have to work through. And at any of these given stages, you might hit a problem that makes you return to an earlier stage, because you just have to say, well, this particular model or this particular approach isn't appropriate. I have to start again from a slightly different base. So that means when it comes to a workflow, it has to be iterative. We're not starting with our best final model, because there's a lot of ways to get to a final model. We want to start with something simple, something easy to test, and we want to build up to a final model, but still in a systematic way. So when it comes to the principles that we want to follow during this process, So one, we want something that is systematic. So the decisions that we make along our pathway of building up our models and building up our model complexity, we want them to be based on evidence-based guidance, or at least something that you have been transparent about in the modeling process. Again, we want these workflows to be flexible. So we want you to have steps that you can follow systematically without having to sort of adjust and force your model down a particular path. However, one of the really key things that we emphasize with Bayesian workflow is this idea of practicality. So one of the additional complexities of Bayesian inference is this idea of it does take somewhat more resources than our frequentist inference or just basic optimization. We do have this extra sampling that needs to be done, estimates to be stored, things like that. So your time and your resources, they're not infinite. So while you can follow a process that can get you to the best possible model, we want you to get to the model as soon as possible. We don't want this to be, months of iterating, testing, coming back and forth. It has to be a robust but yet practical process. And that's where this concept really gets emphasized, this idea of if you're going to fail at some point in the step, if your model is going to at some point be found to not be appropriate, you want to find out as soon as possible, and you want that to fail as quickly as possible in those steps. So this is the idea of failing early and failing fast. So when we talk about some different examples of how a workflow can look, you would have seen Box's loop from Celia's talk this morning. And we can see that it briefly follows it roughly follows these same steps of building a model, making inference, and improving or changing it. However, while this workflow is in some ways very effective in its simplicity, it is quite simple. So in each of these steps, there are a lot of different ways to build a model. There are a lot of different ways to criticize a model. And we want people to know, well, this is the way that I should criticize this particular type of model that's the most appropriate, that's most evidence-based and robust. So unfortunately, while it is a great introduction to a workflow, we need something that is a bit more comprehensive and something that is a bit more robust. So this is what led to a paper by Andrew Gelman, my boss Aki Vetteri, and several others around the idea of what a Bayesian workflow should look like and what steps it should follow. So these steps covered both the ideas that were popularized with Box's loop, but also within each of those steps sort of built up different pathways you can take of how you can build these models, how you can test them, but also during each of these processes, how you can know very quickly when a model isn't appropriate and when you need to iterate and start again. So this idea of identifying very early on whether your model might be misspecified or inappropriate, and also identifying in this computational numerical approximation that is Markov chain Monte Carlo, how confident can we be that our numerical estimation is free of bias, or is at least low enough in bias for us to have confidence in the inferences. Unfortunately, because this is a much more comprehensive, complex process, it doesn't give you quite a nice, simple image like Box's loop. You end up with something like this. Don't try to read everything on the slide unless you're very impressive. We'll be covering through each of the steps. Okay, so what have we done so far? So at this point, we've established why we want to think like a Bayesian, what the benefits of Bayesian inference can be. And we've also introduced the methods that we'll be using for our Bayesian models, and hopefully I've given you enough foreshadowing of some of the things that we'll be diagnosing. And I've also introduced the steps that so the program and the workflow that we'll be following as part of this. So now that we've covered sort of this foundational theoretical background, how do we take this sort of abstract concept of a systematic workflow and put that into practice to solve a real-world problem? So let's say, for example, that you were an analyst for a drug company. If you have higher moral standards, you might just be a university academic. And you've completed a randomized control trial for a drug for epilepsy. So it's a smaller sample, which is quite common for a lot of these trials. Repeated measurements, and also two covariates to consider: the age of the participant, and also the number of seizures that the person is having before they started taking the drug. So what we want to apply a Bayesian model to estimate is there a difference between our treatment and our control groups? Is there a reduction in the number of seizures between our treatment and control groups? So to do this, we're going to be applying our Bayesian workflow, here a little bit larger, so you can try and see a little bit more of it. Now, before I get into the actual steps, so again, something that I want to emphasize is if you look at a lot of these arrows, you'll find that a lot of them, they start looping back to earlier stages. Because again, it's this idea that your model building process, it is iterative and stepwise. Just because you start with a model doesn't mean you're going to end with that model. So, speaking of the model that we start with, how do you pick an initial model? If you're not just going to start with the most complex targeted, how do you know where to start? So, really the best place to start is your hypothesis. What do you think is going to happen? What do you think the relationships are? Now, in our case, we have a treatment trial and we have some covariates. So, we are expecting some impact of age on efficacy of the drug. We are expecting that people that have more seizures will see greater benefits of the drug. Because if you start a trial having 2 seizures, well, you can only reduce by 2. But if you start a trial having 10 seizures, you can reduce by a whole 10. Of course, we expect the number of seizures to change throughout the trial. And this is a key term here. We expect this change to be different between the treatment and control. For those of you familiar with this kind of modeling, this is an interaction effect. So our coefficient is different between the 2 values of these 2 covariates. So because we're looking at a model where we have our covariates and predictors affecting a single outcome, it's natural enough to just start with a linear regression. In this case, we might just start with a simple, normal linear regression. So we have our outcome, which is our number of seizures, and we also have our predictors. So we have our initial model here. This is our observation data, our likelihood, or if you prefer, Avery's personality. Now, how do we take this observation, this likelihood, and how do we turn that into something that we estimate in Stan? So the first thing to do is, well, let's just write out our data log likelihood. So we have here a normal distribution. So for each observation, we have the intercept of our linear regression. Oh, that's skipping ahead. We have our vector of covariates here, so time, treatment, the interaction. We have the coefficient for each of our covariates. And we also have our residual variance here. Got to stop doing that. And you'll also notice up the top here, so it's not just looping over n, it's looping over n times t. So because while we have n participants, we have multiple measurements per participant. So each person has t observations. Okay. And then for those not familiar with this notation, this is just a vector product, which is just equal to the sum of each of these terms. So to translate this likelihood into Stan, we have to talk about what a model even looks like in Stan. So Stan models are specified in blocks. So there are 6 possible blocks. I did just have to count that. For the session today, we're only going to be covering a subset of them, but it's helpful to know that there are those different options. So to start with, let's just have a look at the data parameters and the model block. Hopefully quite self-explanatory there. So if we have a look back to our joint log likelihood function and all of our terms here, what do we think that we're going to be putting into our data block? What are our fixed known values from this expression that we can pass in as data? Yes, N and T, that's good. Anything else? That is possible. In this case, we are estimating sigma, so it wouldn't be data. But in a lot of cases, you might have a fixed residual variance or standard error. For example, meta-analyses are quite common for that. All right, so we have N and we have T and K. Very good catch. So there's two more things to be passed as data. What do we think? Yes, and one more thing. I might ask someone else in the room for the next one, but thank you. Yes, so we have our fixed values here, so the numbers of each of these dimensions, so people, observations, and K, so covariates. We have our covariate matrix here, and we have our outcome here. So Y here is just the number of seizures at each of our assessment points, and X is for each person, for each of their T observations, those covariates, so age, baseline seizure. All right, so that covers our data, our fixed values. So up next we have our parameters. So these are our random values, random variables that we're going to be estimated. What do we think that they are? Hopefully someone new in the room, no offense. What was that, sorry? Yes, alpha is one. And beta, and one more. Perfect, alpha, beta, sigma. So we have our parameters here. So a couple of things to note. So one, we have explicitly declared beta as a vector. So this is an example of some of Stan's typing. So we have both scalar types, so whether something is continuous or discrete, so int and real. But we also have container types, so vector, row vector, and matrix, and different arrays or containers of those containers. So that allows you to work with different matrix expressions and linear algebra. So the other key thing to note here is this term on sigma. So a really nice thing with Stan is that you can impose constraints on your parameters. Can anyone tell me why for sigma we might want to have a lower constraint of 0, a lower bound of 0?
I mean, because they can't be negative seizures, it just in case there is this estimate of 0 probably for a particular.
So yes, there can't be negative seizures, but that's not quite why we've got a bound on sigma here. In the model, what does sigma represent here, sigma squared? Yes, not in a Bayesian sense, but yes, there is uncertainty. So this second parameter of the normal distribution, it is a variance, and how does that inform our bound? Yes, so because we're working with a normal distribution and we're estimating a variance can't be negative. So we have a lower bound. All right, and now finally, the last element here, the model block. So here is where we specify our actual observed data likelihood. All right, so we've covered our fixed data and our parameters, and now we have to use those to specify a likelihood. So given that we're working with a simple linear regression, what likelihood are we using? And I did mention it just before and gave away the answer, but yes, we are working with a normal distribution. And you can see here it is the sum of the log over each of these. So because on the natural scale, it's the product of each of these for each person. Now, as I mentioned earlier, Stan has a lot of support for vectorization. So we don't have to enter this as a loop over these values. We can just say this entire vector is normally distributed with this mean, so our linear predictor term, and this standard deviation. So Stan works with a mean and standard deviation, not mean and variance. So that's why this is sigma, not sigma squared. So something to keep aware of. And also, Stan, the distributions are automatically on the log scale, so we don't have to say this is log of this. So that can make it a bit more convenient when you're specifying your models. All right, so that's our data, our parameters, and our likelihood for our observed data. But we've just spent an hour talking about how great Bayesian inference is, and there isn't a single prior in the model. So we might want to fix that. Oh, sorry, I got ahead of myself. So something that you might also see is, so some of these specialized distributions for regression models. So in this case, because we're working with a linear regression, that is the same as a generalized linear model with an identity link. So a normal identity link, generalized linear model. And we can specify each of our terms independently here without needing to write it out like this. And I'll touch on why that's very beneficial towards the end of the presentation. So hopefully this is also very effective foreshadowing. Brilliant. Okay, so prior information. Don't be discouraged that we're still at the first step. I'm sure the rest goes very quickly. Okay, so ideally with prior information, we would want to be looking at, previous literature. Maybe if we are a drug company, we've done pilot studies with fewer observations or smaller samples, and we would use those to help us derive the priors that we want to use. We would pick priors that are informative in the way that sort of they help guide our inference. However, we're just going to say for this case that, well, we're either a very poor drug company or a very new academic. We don't have any pilot studies and we can't find any literature on treatments for seizures somehow. So instead we'll use what are called weakly informative priors. So you might have heard the term before, diffuse prior or uninformative prior. So these are where you have uncertainty just across the entire real line. So you're saying that your parameter could take any value from negative infinity to positive infinity. It's completely uninformative. However, as we touched on earlier, if you don't have a strong observational likelihood, if you don't have strong influence of your data, well, then your prior is going to have influence on your inferences. So if you use these very, very wide uninformative priors and you have few observations or very complex models, you can inflate your parameter estimates because it can take such a wide range of values and you don't have enough observed data to say, well, none of the values actually get that large or that small. So instead, weakly informative priors are this idea of, well, we're not going to say we have confidence that our value, is here in this distribution, it's 2 or it's 1. We're just going to say it can be anywhere in this range, but outside of that, it's very, very unlikely. So we're not giving any weight to a particular value. We're just saying it's unlikely to take on impossible values. So in this case, we'll use normal priors with a mean of 0 and a standard deviation of 5. For our covariates. And we use a half normal for our residual variance because it's a lower bounded at 0. So, in other words, and also a normal prior for our intercept. Now, at the moment we have exactly the same prior for every coefficient for our 5 covariates, so time, treatment, age, baseline, treatment and time. Does anyone see any problems with that? Why? Yes.
It depends if some of the variables have 5 different deviations, then it might not make sense to make the price on the same scale.
Yes, exactly. So different scales of your covariates. So for example, one of our covariates is a treatment group, 0 and 1. The other one is age. It goes from 50 to 70. So depending on the scale of your covariate, the scale of what's being modelled, what might be a very weakly informative or uninformative prior for one parameter can be extremely informative for another one. Yes. Oh. Yeah. Yep. Perfect. All right, so now we take the same approach to integrate this into our stand model. So we want to now specify our joint log likelihood function, including our priors. So if you remember back to the earlier slide with Bayes' theorem, we have our observed data likelihood, and now we have our priors here. All right, so at this stage, would anyone like to guess what part of our stand model we're going to change? Hopefully someone that hasn't been reading the slides. So what we're going to change is our model block, because that's where we're specifying how we're using our data and our parameters to specify this joint log likelihood function. So we take exactly the same approach, where we have our prior specifications, and then for each of our covariates here. Perfect. All right. So that's the process of going from a prior and a particular observation model to a stand model. Does anyone have any questions about the steps we took to get there?
Would the model definition work without priors as well?
Yes, very good question. So the question was, would the definition work without priors? Yes, it would. So for a stand model, if you just specify your model like this, you have your parameters, but no priors, this is equivalent to specifying a uniform prior over the support range of your given parameter. So it's equivalent to a uniform negative infinity to positive infinity for alpha and beta, and for sigma, it's uniform from 0 to positive infinity. Perfect. Anything else?
Would that be equivalent to the physicist model?
Fantastic catch, yes it is. So for example, with the gradient-based optimization, you might just specify your likelihood like this with no particular priors, and it can be optimized in a similar way. Oh, what's that, sorry? The wrong priors? Fantastic question. Yes, the question was, is there a possibility of using the wrong priors? There's a very, very large possibility of using the wrong priors, and that's why we have a workflow step to check your prior specifications. Very good to be thinking of it. Brilliant. Okay, so we have now... Cool. So we've chosen our observation model, we've specified our priors, and we've built a stand model. So now we can fit it, which is what I would say if we weren't going to now take a break for tea and coffee. All right, so if we sort of go back to where we were before the break, so we'd sort of approached our problem, our epilepsy randomized controlled trial. We decided on an initial model for both our observed data, our likelihood, and we've also chosen our priors and specified it in STAN. All right, so we've picked our model, we've had some coffee and some cake, so obviously now we should fit the model and decide whether or not to give this drug a lot of money. Except we probably shouldn't just yet. So again, what I mentioned earlier is this idea of failing fast and failing early. So it's not going to be as much of an issue for a small, simple model like this with these few observations. But if you're working with very large, very complex models, even just running a model can take some time, you know, an hour, 20 minutes a day. If you have to find out at the end of that running process that there's something wrong with your model, you've just wasted that time. So ideally, you want to find out as soon as possible that, you know, maybe I should change this. So one of the things that we can do before even fitting the data is called a prior predictive check. So we take our model and our prior specification, and we just simulate the data implied by our priors. So what this does is this allows us to see, well, if our prior model was the true model, if it was representative of, you know, what we're truly modeling, what would that data look like if it came out the other end? And if that's simulated predicted data, if that is, if it's impossible or if it's markedly different to our actual observations, well, then we already know before we fitted the model that, well, this model probably isn't good for our data. So you can identify before you've spent these hours, these days in computation, well, maybe I should try something a bit different. So to implement this using Stan, all we're going to do is to use one of the other blocks. So this one is the generated quantities block down the bottom here. And this is for, well, generating quantities. So what we do is we take our priors, and what we're going to do here is we introduce a new data argument, and we just use this as a Boolean toggle for whether or not we're actually modeling our observed outcomes here. So if sample prior is equal to 1, then we ignore this block and we're only looking at our priors. And if it's equal to 0, well, then we're actually fitting our model to our observed data. And then what we want to do is that for each iteration of our Markov chain, we use our parameter values and we use our input covariates that we estimated those for, and we use that to simulate what the seizure counts these priors imply for our data. So if we go to our Colab notebook, so hopefully this is all finished setting up for you. I'll just zoom in so that it's a bit more visible. Okay, so if we run this step to download the Stan models that we'll be using, and we'll also load some of the R packages. All right, so if we have a look at the actual data that we're modeling, we can see our various covariates here. I'll zoom in a bit more on that. Cool. So you can see that while we have our treatment, our participant number, and visit, where count here is our seizure count, we have two options here for modeling our covariates, our continuous covariates, sorry. So we have the raw numbers for participant age and baseline seizures, and we also have the standardized values. Would anyone want to hazard a guess why, in this case specifically, we prefer the standardized values?
So we don't have state issues?
Exactly. So because we've chosen the exact same prior scale for each of our coefficients, if we have both of our continuous covariates on the same unit scale, we know that the level of informativeness of our prior is exactly the same for both of them. Otherwise, you might have a situation like this where some people have a baseline number of seizures of 8 with an age of 35 to 40. A coefficient, a prior there that ranges from -5 to 5 is a very different level of informativeness for a value that can be as high as 40, as opposed to a value that it might get up to 7 or 8, if we ignore the outlier down there for the purpose of the example. So an option that a lot of people are using when constructing their priors or choosing a model in priors is they might standardize their continuous covariates, so then you no longer have to consider a different scale for their respective priors. That's not always appropriate. You can run into issues with missing data. So if you don't have all observations and you're standardizing, then you're not standardizing with the full approximation of the population. Alternatively, for when you have train and test data set, you can have issues if you're, it's that data pollution of if you're using the full data set to standardize the training set. So two options, both have benefits and drawbacks. So for this case, we'll be using the standardized continuous, just so we don't have to worry about the priors. All right, so if you remember, we've chosen our initial model and we've picked out our stand code. So you can see I've added here our data argument for sample prior. And here we're using that data argument to decide whether or not we include our observed data likelihood in the modeling. All right, now to pass, so to begin our sampling, we need to actually have the data that Stan expects. So we have our declarations up here, and we just need to restructure our input data set to match what Stan is expecting. Now here you can see I've set sample prior equal 1, which means that we're not including our likelihood, we're just doing our prior predictive check. Alrighty, so what have I done? So if you cloned the repo earlier, like I did, you might find that there are pre-compiled executables in there, because I thought I was being efficient and making things faster for everyone, but Colab doesn't like it. So if you add force recompile is equal to true, it'll ignore the pre-compiled executable and compile it again. Alrighty. So this is following that process of taking our stand code, translating that into C++, and then just passing that C++ to the system's C++ compiler. Now, as you might be noticing, on some systems, this can take some time. So for people that do want to iterate quite quickly, you might prefer an interpreted language, or different packages might be able to code a very flexible model that can contain a lot of different model constructions without having to specify a different model for each. Alrighty, now that I've wasted enough time and that's compiled, we can start the fitting. So given our compiled model here, we're just going to call our HMC sampling algorithm with our data and some configuration for the number of chains and the seed. Now we can see that when we run this, it runs extremely quickly, only 2 seconds. But really the most interesting thing here is our prior predictive check. So now we've fitted our model, ignoring our observed data, just simulating from the prior. And now we want to take a subset of our predictions, because remember we have a prediction at every Markov iteration. And we have that for each chains. So you can see we've run 4 Markov chains. So for 4 Markov chains, we have a prediction at each iteration. So because that can be way too much information, we only want to consider just a subset of them. So what we do is we use this function from the Bayes plot package that we loaded earlier. And what this does is this plots the density of just a subset of those predictions. So if I can get rid of that, cool. So each of these lines is the density of the predicted data set at a given Markov iteration. Cool. All right, so just looking at this, and I zoom in, if it doesn't give away. So looking at these predictions and possibly looking at the x-axis, can anyone say why we might want to reject this model? Perfect, yes. So if we remember that we're modeling counts of occurrences, counts of seizures that have happened, well, our model is saying that just as many negative seizures happen as positive seizures. Obviously, that's not accurate. And if we were to fit our model using this, while we might get estimates that are still somewhat representative, the sampling isn't going to be efficient, the estimates are going to have much wider uncertainty, and it's just not going to be as good a model. But this is an example of, we haven't even had to fit the model to our data, and we've already found out that we don't want to use this model, that this model isn't appropriate. So, yes?
I wanted to know this thing. Even if the prior is wrong here, which is evident from the prior predictive, the prior was still for the coefficient, right?
Mm-hmm.
So we are assuming that the model is wrong regarding the distribution that we have chosen for the coefficients, the alpha and beta, or are we saying that it is wrong for y? That is
Perfect. It's a brilliant question. Yes, the question was, so we're rejecting our model here, but when we reject it, are we saying it's because of our choice of priors, because we've done a prior simulation, or is it because of the model that we've chosen for our outcome y? Which is exactly the 2 slides ahead. You'll be giving this talk next year. So we get to this stage of we've rejected this model, and now we need to consider, what do we change? So do we need to reconsider our choice of our priors, or do we reconsider our choice of our actual data model, our likelihood? So the 2 considerations here are, if we consider our observation model, that's really about thinking about what assumptions are this particular data generating model making? What does it imply about what we're modeling? So in this case, because we chose a normal linear regression, our model is assuming that, well, negative values are just as probable as positive values, at least for our particular construction. So obviously, that's an assumption of the data generating process that is inconsistent with the phenomena that exists as we know it and what we're actually modeling. The second thing to consider is our prior choices. So it isn't the case in this situation, but in a lot of situations, you might find that intentionally or not, your priors can imply impossible values for your outcome. And this becomes even more likely as you have more and more parameters and more combinations of priors. Because it might not be that a single prior itself is inappropriate, but particular combinations of priors and particular combinations of prior influence can result in it can induce a likelihood that is towards impossible or at least unintended values. So now that in this case, we believe that it's our likelihood, our data model that is inappropriate here. Now, we know that we're modeling a count of occurrences, a count of seizures, and we know that a very common model for counts is the Poisson. So that's naturally a very good place to start. So we'll replace our normal data model, our normal likelihood, with a Poisson. And now, because we're no longer working with a normally distributed outcome, we have to construct our linear predictor slightly differently. So what is very commonly used here is a log link. So we model our covariates, our intercepts, on the log scale, and then we exponentiate those before it's given to our Poisson. So that ensures that our linear predictor is always positive, and satisfies the assumptions of the distribution. But this then ties in very well to the question that was asked around how do you know when your priors are appropriate? So in this case, now that we've changed our data model, why is it incredibly essential that we reconsider our choice of priors here? Yes, but it's something about what we've done to ensure that they're positive. I just sort of very subtly circle that. Yes, and why is that important for our priors?
These scales, in question, and no longer have the sample, for example, scale naturally linearly maps onto the outcome, like
Yep, exactly. So because we're now working with a log linker on the log scale, our coefficients, they have different interpretations and different effects. So because now we're on the log scale, these are multiplicative effects. They're not additive. So which means that a much smaller value now, for example, a log value of 0.1, once we exponentiate it, it goes to 1.1, which implies a 10% increase as opposed to a plus 1.1 change. So these are multiplicative effects. So now our priors have very different levels of effect and influence because we're working on very, very different scales, very, very different types of effects. It's not too much of a problem for a model like this with the log scale because it will just then it'll just become extremely wide, approximating an uninformative prior, which isn't always great. But for different types of models and different links, so a very common one is for discrete data, where you're working with a logit link. So the logit link only has a small range of possible values before the link to the natural scale over or underflows, because we're mapping to a probability between 0 and 1. So what we find is that when people, they might adapt from a normal linear model to a Bernoulli binomial with a logit link, and they don't adapt their priors, if they're working with a prior scale that's 0 to 10, well, immediately that's just across the full possible range of values for the logit. It's no longer implying the same thing. So it's really, really essential where if you've changed your likelihood, you've changed your data model, that you make sure that your prior assumptions and your assumptions about relationships in the data haven't changed. Or if they have, that you have accounted for it. So if we go back to our notebook and we try our Poisson with a log link, let's have a look at what we've changed.
In the definition of the problem, it was written y is a sample of Poisson lambda I. That is, assume that each patient has a different Poisson distribution. Otherwise, there would have been just one lambda had it been into the global.
Yes, independent Poissons for each observation.
So in the likelihood, then we are just adding for all the observations for just one patient, and then multiplying this for all the observations of one patient, and then adding all the patients.
So it's exactly the same as what we've done with the normal, but now it's a Poisson. Might just start this recompiling. Okay, so if we have a look at our new model where we're looking at a Poisson outcome with a log link, we can see a few things have changed, some less obvious than others. All right, who can point out what's changed about our parameters that we're estimating? The what's that, sorry? Yes, so there's no longer a specific argument for sampling from the prior. For our parameters themselves, has there anything changed about what's being estimated in the model? Thank you very much. Yes, sigma is missing. So we're no longer estimating sigma, which is because with a Poisson outcome, it doesn't have the same concept of a residual variance. There are different ways to induce that, but very, very beyond the scope of this.
We know normal distributions give possibility of negative numbers.
Mm-hmm.
So if we notice that we don't make negative numbers, then why should we use it in the first place?
Because it's a great example for teaching. So the question was, why would I use a normal model in the first example if it allows negative values? It's because I'm a very good teacher. really shouldn't laugh that much, but okay. Yeah, so of course, the more you know about the assumptions of a particular sort of distribution or data model, you can save yourself a lot of wasted computational steps by automatically ruling out the ones that you know aren't going to be appropriate. And that's really one of these areas where both experience and also expert input can really save a lot of time in the modeling process. Perfect, cool. All right, so we know now that we're no longer estimating sigma in the parameters. What's changed about our data declarations other than the sample prior? This one's a bit more subtle.
It's array vector.
Yes, and it's an array of what? Yes. So this is an example of Stan's requirements for strong typing. So because we're now using a distribution specifically for categorical data, specifically for counts, we have to make sure that we're very accurately declaring the type of data that's coming in. We're saying that it is integer data. There shouldn't be any decimal values because our distribution is not defined for them. Other than that, we follow a very similar process. We construct our linear predictor, and we also use that here to construct our predictions. Now, the very keen-eyed amongst you might have noticed that I'm not exponentiating anything here like I was in the slides. This is because we're using specifically the Poisson with a log link distribution that's in Stan. So by using this specific compound distribution, Stan, because it knows what link we're using, it knows what we're trying to do, it can take that exponentiation internally in a much more numerically stable way. Because when you're exponentiating values, they can overflow to impossibly large values very, very quickly, and that can break estimation. So by using specific compound distributions like this, it can be handled in a much more numerically stable way, both for the values and for the gradients of the distribution, which are just as important. Okay, so we've now updated our model to use a Poisson, and we're using a Poisson with a log link. We've got our same method here for compiling our new model, and now we're sampling. So in this case, I don't have a particular declaration for sample prior because our model doesn't have a definition for it, so it doesn't matter what value it's set to. All right, so now that we've run it, we fit it, and now we can have a look at our new predictions. And I mean, that's fantastic. So that looks like a much more reasonable and realistic range of predictions. There's nothing negative, and yes. So you might note at this stage, we haven't compared it to the observed data. We're just saying, well, based on what we know and what we assume, it seems realistic. There are a lot of conflicting opinions around how actively a role your observed data should play in your model development, and especially prior development process. To be purely Bayesian is mostly to just keep the two concepts separate of you have your prior assumptions and you have your observed data. You can also use your observed data to inform your choice of priors. You can use your use your observed data to inform your choice of model. So for example, here we have our predicted seizures having most of their values smaller than 25 and with a peak, let's say around 5 to 10. What I could do here is I could look at my observed data to say that, well, is that accurate? Is that realistic? And if these priors don't match with my observed data, then I could just throw that away and start again. So.
What's your opinion? Is the actual
Did you have to say that while I'm being recorded? The question was, what is my opinion on the right one to use? I'm very much a practical Bayesian. Whatever's the most efficient approach, I wouldn't go towards the scale of using your observed means and standard deviations to set your prior means and standard deviations. But in many situations, you will likely have to look at your data in some way to inform your choices. But really the key thing to emphasize here, and both in the workflow in general, is that you're not doing it in a way to sort of nudge the model building towards a particular conclusion. You're still following a particular systematic and rigorous process, but you might be including steps that some people might disagree with. Yes. All right, so yes, back to my slides. Cool. All right, so we have our new check that is much better. So the next stage, now that we have our a model that we're happy with and we fit it to our data, pardon me, we can finally move to the next step of our workflow. So let's say that we've taken our model and we fitted it to our observed data. We have our full posterior using both our prior and our observed likelihood. Now that we've run the model, before we even start interpreting the estimates and using the results to make decisions, how do we know that we can trust them? How do we know that our sampling has been efficient and accurate? Because remember, the sources of bias from MCMC that I mentioned earlier, whether it's found the target distribution and whether it's fully explored it. So you might have a very complex posterior that is hard for a sampler to explore, and if you haven't run your chain for long enough, there might be parts of your posterior that haven't been found and aren't being considered in your inference. So there could be tails of your distribution that could affect the decisions that you make, and if you haven't sampled efficiently and comprehensively, you might not be considering those. So the methods that we use for diagnosing these are a combination of both graphical and statistical. So graphically, we consider what are called trace plots. And these are really just a graphical depiction of how the chains have sampled, or the progression of the chains through the distribution. So if you consider almost flipping this plot on its side and say that this is the x-axis, and you can almost imagine that this was a distribution, a density here. We can see that our sampler started in some very strange far off points, but then eventually it's now very closely focused around here. So this first stage, this is that point of the sampler. We've started it in some sort of diffuse random place in the probability space, and through the magic of Markov transitions, it's found our probability mass and it started exploring. So you can see this red line here. So this sort of depicts the range of values that we would consider as warm-up, or you might also hear the term burn-in being used. And we generally just discard this first half of the sampling so that they don't influence our inferences. Right, so when we look at these trace plots, what we want to see is that when you have multiple Markov chains, that they've all found the same range of values. You don't have one chain that is sort of sampling up here, one chain sampling a little bit down there. They've all found the same probability space of the probability mass, but also that they've all explored it comprehensively. So ideally, you might see something we would describe as a furry caterpillar of a fairly thick sort of trace plot, where still the sampler has gone to the bounds, but it has multiple times gone back and forth. So when we're happy with conversions, when we're happy with our trace plot, we want something that says, well, all of our chains, they found the same probability mass, and they all seem to have explored it fully. It doesn't look like there's some probability mass that's been missed by some or any of the chains. Now, just because things appear sufficient graphically, it might not always be the case statistically. So we like to supplement these with some statistical checks. You might have heard these described as the R-hat statistic, which is the variance within chains compared to between chains. And what we want are values near 1 for our R-hat. So, which all that says is that the amount of variance of a particular chain sampling is consistent with the amount of variance for the other chain sampling. There are a few different ways of calculating the R-hat, so you might see small differences between different packages. Just something to be aware of. Cool. All right. Now, beyond trace plots and convergence, there's still the question of, just because all of our chains, all of our sampling chains have found and explored the same region of the probability mass, does that mean that we still have sufficiently informative samples to be able to base our estimates off? So this is really important because the assumptions behind an MCMC estimator assumes that each of our samples are independent. Now, the longer you run your Markov chain for, the more independent samples that you will get. But depending on the distribution, depending on the particular construction of your likelihood, you can end up with very highly correlated samples and not very many independent samples. So we use this statistic called the effective sample size, which gives you an estimate of the number of truly independent samples from your Markov chain. Gives you an estimate of the number of truly independent samples you would need for the same amount of uncertainty that you're currently observing. So if you have, let's say you've sampled for 4,000 iterations, but you end up with an effective sample size of 50, well, it's saying that you've really only got 50 effective independent samples to base your inferences off. So when we see such low effective sample sizes, not absolute, but relative to our number of iterations, that's a sign to say there's something about our sampling, there's something about our construction of our distribution that we need to investigate. Now, we evaluate this in two forms. So we look at both the bulk effective sample size. So this is the main body of our posterior, the main region where the posterior mass is found. And then we look at it in the tails, so the very high and the very, very low values. Because you might have a posterior that's very easy to sample in the middle, but then when you get out to the tails, your sampler really struggles and you haven't got very good quantification or exploration of those tails. And if you're making inferences based on the tails, that's really important to know. Right. So if we have a look at how that looks, so we can generate our same trace plots here now for each of our covariates. And if we want to have a look at our convergence statistics, so we can see our R-hats here for each of our parameters. And here we can see our effective sample sizes, both for the bulk of the posterior and also for the tails. So because we ran our sampler for four chains, and now the defaults here are 1,000 iterations per chain post-warm-up. So here we're looking at 4,000 iterations compared to an ESS of 1,500, 3,000. In most cases, I'd say that's not too bad an ESS. Like, it indicates that sampling is acceptable. There aren't very many good, robust heuristics for when that discrepancy between iterations and effective sample size is large enough to be concerning. In most cases, you'll likely only investigate it when it's very, very obviously too small, like if this was down in the 200s or the 300s. But it's still very important to be aware of, especially if you're comparing models and comparing inferences between models, if they have very different effective sample sizes. All right. Well, that's getting ahead. Okay. Do you have any questions about this stage of convergence and checking?
How is this count estimated since starts?
The effective sample size? Yes. Oh, you're testing me now. So it's based on the autocorrelation between samples in the MCMC chain, but it also considers multiple chains, I think. I'll put the reference in the Slack channel for the different approaches that are used and the ones that one that's currently used in Stan, the bulk and the tail in the Slack, because I don't want to give you the incorrect answer, but I don't know off the top of my head. Cool. Do we have another question?
So we want the trace plot to be the second type one or the first?
So both of these trace plots are the same. In fact, they're actually exactly the same. So this trace plot here is just this second half here after this has been thrown away, which is why we sort of discard this to reduce this bias. Some people might ask, why throw away half of the samples? Like, isn't that a little bit aggressive? The true problem is that we don't know how long it took the sampler to get to the probability mass. So it's often safer to discard more and then sample more so that you're quite confident that there aren't any out of probability samples that are being used. But also for HMC and nuts specifically, this warm-up phase is used for tuning those parameters for Hamiltonian Monte Carlo. So the longer that you run your warm-up for, the more tuned your sampling can be. So you don't always want to cut it too short. But on the other hand, on the more practical side of things, for models that you are confident that you're finding the probability mass quickly, and you need it to run quickly or many, many times, a lot of people will then just reduce that number of thrown out samples. They might just discard up to sort of this point so that they can still have large numbers of iterations without having to fit for as many post warm-up. But it's always something to diagnose before you make that choice. I really should have an example. So there's a few different kinds of undesirable trace plots. So one can be where you have, we call it non-identifiability, where you might have different chains have converged to different parts of the parameter space completely. Non-identifiability or multimodality. So you might see here that, well, yes, this chain has converged to this particular distribution and it's sampling it tail to tail. But what if you had a distribution with multiple modes where it has, multiple regions of mass that can be sampled? Well, you might find that one chain has converged to one mode, and you might find that one chain has converged to another mode. And maybe very infrequently, your sampler has moved from one mode to the other. So you can have one chain here, one chain in the middle, and you can even have one chain that starts down low and then jumps up to the other one as it finds the other mode. And that can be quite a tricky problem for both inference, where statistically it looks like your chains haven't converged, but really they have converged just within separate modes. And you might want to combine your chains, or they call it relabeling to be able to quantify which mode is which. Alternatively, you might experience something that's called poor mixing, where instead of a trace plot that looks like this, where you can see very quickly it's gone up and down and up and down, you might have a sampler that takes quite a few iterations to get to each side of the probability space. So you'll see it wander up to the middle and then down and down. So even in the same 4,000 iterations, it's only hit each of the tails 2 or 3 times. And that's a sign that you might need to adjust your model so that your sampler can explore it more efficiently. You might need to look at a different approach to sampling. Yes, that can be quite a tricky problem. That's also a situation where you see this approach thinning used, where if it's taking 1,000 iterations to get to each tail of the mode, people will just throw away 1,000 iterations in between so that they aren't getting that trace plot like this and just throwing away all the steps in the middle that they don't need. Sure. Right. Do we have any other? Yes. I'll do this and then come back.
In the more classical statistical testing paradigm, there's a lot of, I'd say, anxiety about whether we're doing too many tests so that we'll find some spurious result. So many hypothesis tests that we at least one of them will work out. In this kind of circular Bayesian diagram, it seems like we have the luxury of kind of changing the model, the parameters, rerunning the refitting and going around and around. Is there the same risk? And if so, how do we avoid that in Bayesian paradigm?
Absolutely. Fantastic question. So, so the question was, traditionally with a lot of statistical testing, there's this problem of if you keep testing, you'll find something significant and you might just keep testing to the answer that you want or adjust to the answer that you want. And that's exactly the kind of problem that the workflow is trying to solve, where there are a lot of different ways for the workflow to go, but it's very systematic on why a step was taken in a particular way. It's not just, I took this step because it seemed a bit better. It's, I have this reference that says, well, this is the most robust step to take. There's also a lot of work now into what's called multiverse analyses, where while there are all of these different decisions you can take during the analysis, there's multiple different models that you could have ended up with based on the different pathway that you chose. So what they do instead is they fit every possible pathway to see, well, depending on which particular analysis pathway I chose, what was my model and what did I conclude about the estimates? Like, did I conclude there was an effect of the treatment just because I was very likely to end up with this one model? So that's a very long way to say there's no good answer. Yes. Yes and no. So a lot of sensitivity analysis also suffers from the same problem of, well, really, you can just adjust in a particular way to get a particular result of, like, why did you choose that particular prior for your sensitivity analysis? Why did you choose that different distribution? But again, there's so many different choices, and you need a robust way to say, I chose it because of this, or there's the post hoc of, these are all of the different choices. I didn't have an active role in which one. So it's, yeah, a superpowered sensitivity analysis, basically.
One question, I would like to come back to the multimodality. If we see that the multiple modes in our posterior, we say it's fine if we adjust maybe our model to already include the multimodality so we can maybe get rid of that in the posterior.
Oh, that's a very good question. So the question was, should we adjust a model if we see multimodality? And that really comes back to what you want to use the model for. If you're making inferences based on, like, the intervals of your coefficients or your quantities, those aren't likely to be accurate if you have multiple modes. Again, same if you're making decisions around whether your model has converged, it's not accurate with the multiple modes, or most generally not. But on the other hand, if you're if you're using the model just for predictions rather than inference, in a lot of cases, the multimodality isn't a problem. That's a big generalization, though, so it should also be diagnosed. And the other problem is that a lot of the solutions for solving this multimodality can induce additional restrictions, like forcing the model to be positive, forcing there to be a particular ordering, and that's, again, introducing additional assumptions to the model. So there's both benefits and drawbacks to either approach. Cool. We had one more question here.
You mentioned that sometimes the test plot can look like it took a lot of samples to travel from tails. So does it happen when the output space is really high dimensional, or like the input space is really high dimensional in that case, or when is the possibility of such a thing?
So the question was around when would we likely see this poor mixing of it taking so long to get to either side? There's a few different places that it can occur, not always in very high dimensional posteriors, but sometimes frequently. That's very conflicting. Some place where you're quite likely to see it is if you have a very tricky posterior where you have regions of the probability mass where the sampler needs to take small steps to still be in the probability mass, but then you have other regions where the probability mass is very large, so it could have taken bigger steps and explored it more efficiently. So if the sampler adapts to take very small steps just to get through this one tail, then it's going to take a very long time to get to the other end, taking those tiny steps. And that's a space where alternative approaches to adaptation have been proposed, or alternative approaches to this sort of rejection if it jumps outside of the distribution have been proposed, but still nothing very perfect.
We could also assume that if this thing happens, then the posterior has a back tail.
I wouldn't say you should assume it. It's very hard to make particular assumptions about the shape if you haven't fully explored it. It's just something to be aware of, that you likely need more samples to have any confidence, to have confidence.
Another assumption that seems quite important is that the samples are independent.
Mm-hmm.
Is there a way to apply something like MCMC if we have, let's say, like a time series that exhibits some autocorrelation?
Absolutely. So, yeah, the question was, this assumption of the samples being independent, can it be applied to dependent data? So the key thing is the distinction between the model and the samples. So the Markov chain samples are assumed to be independent, but what you're modeling isn't assumed to be independent. So you might have a model that assumes it's actually perfect. So here in our epilepsy data, we have multiple assumptions. So we have multiple observations per person. If I get right back to the very start. So this is not independent data because it is repeated measurements, but the Markov chain assumption is only about the samples from the distribution. It's not about the actual problem that we're modeling. So whether you model it as dependent or independent, that is in itself independent of the Markov chain assumption. Okay, so we've fitted our model. We've validated the fit. So we've checked our convergence and we've checked our effective sample size. They're not fantastic, at least on the effective sample size, but we're happy enough with it for now. So if we don't have any problems with the actual computation, now we can move on to criticizing the model further. Do we want to say that this model is accurately representing the data? So a very good first step here, and again, first step being because it's computationally cheap and will fail quickly, is the idea of graphical posterior predictive checks. So whereas before we were simulating data from our priors, now we're simulating from the posterior. So considering both our observed likelihood and our priors, what does that imply about the observations that we should be seeing? If our posterior is a true representation of the distribution, true representation of the distribution of the effect, does it recover our data well? So as before with the prior predictive check where you had plotted densities from each iteration, we now do the same thing, both considering our prior and our likelihood, but now we also plot the density of our observed data to make sure that it matches. Something that I will say here is that not every graphical posterior check uses density plots like this. And to be completely technically accurate, this isn't the best check for this because it is discrete and it's using KDEs that have particular assumptions. So when doing these kinds of checks, it's very important to look at sort of the different recommendations for the data that you're using and also for the relationship that you're assessing. But just didn't have time to cover too many concepts today. But at the end of the day, they all assess the same kind of ideal. Is the data implied by our model consistent with the data that we've observed? And if it isn't, what do we need to change and should we change? So if we apply the check to our data here, we can see that our model is predicting a greater density of smaller counts, so fewer seizures than we've actually observed. So it seems like there's something inconsistent with our observed data. So like we did with our data likelihood, when we had our normal, we reject our model. Don't get disheartened, this happens quite a lot. So now that we've rejected our model, again, where do we go from here? Well, at this stage, we're fairly happy with sticking with our Poisson and sticking with our sort of discrete modeling. So rather than throwing away the entire data model, we might just try and make things a little bit more accurate, tweak things a little bit. So it's at this stage we start considering what particular assumptions that our model is making and our approach to modeling is making. So one thing to remember is with a Poisson, it's assuming that the quantity being modeled has an equal mean and variance. And in this case, we can see that because there's such a large tail here, there is likely to be a difference between the mean and our variance of what's being modeled. Additionally, we haven't accounted for the fact that we have dependent observations. We have multiple observations from the same person as they've progressed through the trial. So that means when we're modeling each observation as independent of each other, we're ignoring this whole other level of information that's available. So to help add some flexibility here and to help account for that dependence of repeated observations, we'll add a randomly varying intercept, a random effect. Now here I've chosen a gamma distribution with a single parameter. That's not a very standard approach. Most people would start with a normal distribution, but you'll see why I chose this in just a second, if you can trust me for that long. And again, we have a prior for our parameter here, and we're specifying a half Cauchy. So here the positive indicating that we've constrained this parameter to be positive. So if we have a look at how we would specify this in Stan, so everything else about the model is the same, our observed likelihood, almost, and our linear predictor, except now we have a random intercept, a random effect. So to see how this looks in Stan, we now have a parameter for our gamma variable. And now we have for each n individual, each person, we have their own unique random intercept. So this allows the multiple observations for that person to be modeled from a single distribution, or to have that dependence accounted for. And you can see here we've specified our gamma with the single shape parameters. Now, we do have to slightly modify our data to fit this, because now we need to know for each observation which person is that repeated measurement associated with. So we add an indicator that says, for this observation, it's person A, it's person B, it's person C. So very, very minor. We just add another entry saying, this is our patient. So we compile and fit that. It's going to take a minute, so you can just trust me that these are the results. That's a trick, don't trust anyone. So when we have a look at our new model, we can see that including this additional randomly varying intercept, the gamma distributed intercept, it's now much more accurately capturing our observed data. It's much more accurately capturing across the full range of values. And that means that if we wanted to make inferences about our treatment effect or particular relationships based on this model, we can have a lot more confidence across the full range of values, rather than saying, well, this model only reproduced it well for individuals with seizures 5 to 10. Finally, fantastically, we are at the stage where we accept the model. So we're happy with our model for our likelihood. We're happy with the priors that we're using. Where do we go from here? Now, this is really a question that comes back to your particular aim and goal in your modeling. So if you just want to interpret quickly, if you're confident that the effects that you've estimated are accurate and robust, and you're fine to stop there, then that's also completely fine. If, on the other hand, let's say you are working at a drug company and they want to take this model and they want to use it in some sort of analysis pipeline, and that model is going to run every minute, every hour for the next 2 months. Well, then the emphasis is going to be, well, we have a model that is now accurate and a good model of our data. How can we take this model and make it run more efficiently, make it run faster, without having to compromise too much on our predictions or compromise on our accuracy? So if that was our goal, we could then say, well, we've improved our accuracy by adding an additional parameter for each person, this random intercept. Can I get the same benefits, the same accuracy, without estimating one of those for everyone? And the answer is, thanks to the magic of mathematics, yes, you can. Never thought I'd say that sentence. So approach you can then take is having a look at something called marginalization. So this is a way to construct the same posterior density or the same distribution without always needing to estimate the same number of parameters. So in this case, we have our fantastic accuracy using a gamma distribution for each person. Now, what we know is that when we have a Poisson and we have a gamma distributed effect, the single parameter, we know that if we integrate that effect out, integrate across the full range of values that parameter can take, that's equivalent to a negative binomial parameterized by the mean and dispersion. Now, as I said before, trust nobody. So we can also verify that numerically. So let's say, for example, we have a completely arbitrary linear predictor. We have a particular number of seizures and our shape for our gamma. Now what we want to do is take the likelihood we're currently using, so this is our Poisson with our linear predictor and our intercept following a gamma distribution, and we want to integrate that likelihood from 0 to infinity for our theta. So what we find is that when we integrate that parameter out of the likelihood, we end up with exactly the same density as we do with just a negative binomial. So now we can fantastically impress our bosses and give them exactly the same model, exactly the same likelihood with n fewer parameters. So if we have a look at that, so now you can see that our parameter block is almost the same, except now we've stopped at U-shape, we don't have an additional n parameters, and now we've changed to a negative binomial. The negative binomial 2 here is the mean and dispersion parameterization. And I'll get that running. And again, if you trust me completely, we can see that this new model, our marginalized model, gives as good a fit, pardon me, as the one that we had before, but it does it in significantly shorter amount of time because we have so many fewer parameters to estimate and to estimate gradients for as part of sampling. All right, now at this stage of our workflow, do we stop? Do we accept the model? Or do we keep chasing a promotion? Always chase the promotion. So now that we have a likelihood construction that we like, we can then start looking at, well, what can we do to tune this a bit better based on the tools and methods that we're using? So because we're using Stan, and because we're using Hamiltonian Monte Carlo, we know that we're relying on gradient calculations. So that means that when we're calculating our likelihood, we need to calculate the gradient with respect to each of our inputs. And when you have terms like we do here in our linear predictor, this means that we have to construct and propagate gradients for each term of this multiplication of x with beta. Now, this ends up with an additional n times t gradient calculations because we have n times t observations. But we know that at the end of the day, we don't need the gradients with respect to x. We don't need that n by t. We only need gradients with respect to beta and alpha. So we can take advantage of some of the specialized tools which say that, well, for these inputs that are data, well, let's just not calculate gradients for them. Let's only calculate it for the parameters themselves. Now, if you remember one of the models from earlier, it was using a GLM distribution, the normal ID GLM. Well, we can do the same thing with our negative binomial. And we use our GLM distribution for our negative binomial outcome. We run and fit that. And if we then have a look, again, exactly the same fit, expectedly, but now we have an even faster improvements in our time. So at this stage, we're not going to keep iterating. That's probably fine. We get the promotion. But this is an example of just because the workflow exists of iterating and returning, again, you really have to consider what your goal is as to when you stop. Because it is possible to keep on iterating, keep on perfecting. But if really you're just interested in inference for a treatment effect, well, you don't need to optimize to perfection. Like, you can stop once the model is sufficient. That's a very open question of when the model is sufficient, but it's always very important to keep in mind what your goal is when you start going through these steps. So when it comes to actually comparing these models, now it comes back to what were our inferences about our treatment effect? Well, unfortunately for our Poisson model, we can see that our intercept crossed 0, and we can say, well, likely no effect, but we have a very small effective sample size. So we can't have a lot of confidence that this is a very accurate representation of, an accurate quantification of our target distribution. But if, on the other hand, we have a look at our negative binomial, we can see that even though our intervals and our conclusions are broadly consistent, the effective sample sizes are much larger, so we can have more confidence that these are the accurate predictions. There is likely to not be an effect. So in this case, you might look at those +1 values and think, well, maybe I do have to keep iterating. Maybe I do have to go down this route of finding something more accurate. So just because you might feel like you've gotten to the end of the step, unfortunately, there's always an arrow to bring you back to an earlier step or back to the very start. So at the end of the, once we finish up, we tell our bosses, we'll go with a negative binomial. We can use it in production. It's quick and efficient. And also, it seems to have accurate estimates. It won't always be that clean a trade-off. Quite often, there will be a greater discrepancy between efficiency and accuracy. So something to be aware of that at some point. You won't be able to iterate to this level of optimization. All right, so I did skip past this. Did we have any questions around sort of this process of taking the inference from these models or the steps that we've gone to this far?
What if further down the line we have multiple teams doing the same work, and they find comparatively equivalent results? This is what we call observational equivalence, and how do we solve it with Bayesian framework?
Could you say that again, sorry?
So basically, we have multiple models that perform the same regard
Mm.
to the data, without, say, imposing a structure on top of that. So how do we say which model is best for designing our data?
Good question. So the question was, how do we know which model is a good representation of the data if we're looking at multiple? There are a lot of different assessments for fitting to data and comparing between models. I kept it very simple with the predictive checks, but there's a lot of power and robustness in cross-validation methods, leave one out and leave one out approximations. There's a lot of great efficient work in the Bayesian realm for that. But also there's this idea of you might not even have to choose between the models. You can combine models and get the power of both of them through things like Bayesian model averaging or model stacking. You can also look at model expansion. So rather than sort of combining the inferences of these two models, well, could you just have one single more complex model that includes both of them? You might not always need to have the smallest, most efficient model if that's not really your goal. Okay, so that takes us to the end of our workflow pathway. There is not another arrow to take us back to the start. So the key takeaways that I want you to take from this session is that Bayesian inference and Bayesian computational methods themselves are both very powerful additions to your modeling toolkit. There's a lot of flexibility and power that you can add to both your inferences, your analyses, and the approaches that you take to your modeling. But also, they come with a lot of extra complexity and a lot of different choices that you can make to navigate that complexity. And it's always recommended to try and follow some sort of structured, rigorous, and systematic workflow when you are making those decisions so that you're not accidentally introducing bias. And this is an area where there's a lot of ongoing work. So if you just Google Bayesian workflow, you'll see a long list of references, most of them with my boss's name on it. He's very active. But yeah, so it's something to keep very strongly in mind when you're following these analytic processes. And with that, thank you very much.